Hello everyone, today we will talk about chirality or the handedness of a molecule. So some molecules are just like our hands, they are mirror images of each other, but they are not superimposable. So you can try to see they are mirror images, but no matter how much you try, you cannot superimpose one hand over the other. So the handedness or the chirality of a molecule comes from the asymmetry in the three-dimensional arrangement or connectivity of constituents with respect to a tetrahedral atom. And when we're talking about tetrahedral atom, we're just not looking at carbon. Some other atoms with a tendency to have tetrahedral geometry can also be a chirality center. We know that the molecule is handed when we try the mirror test. For example, we have this set of molecules right here with three distinct constituents bonded to a tetrahedral carbon. So one would be the white atom, and then the green one, and then the red one, for a total of three constituents bonded to a tetrahedral carbon. So that means 4 bonds. If we try to generate its mirror image, we will have this other molecule. Wait now, let me just generate it. Okay, so let's pretend there's a mirror here, and we generate its mirror image. And to check whether the molecule is handed, or what we formally call chiral, we try to superimpose the two molecules by rotating one of them with respect to one of its bonds. So we know for this molecule that it's very easy. So to force them to superimpose, so if we do that, it's already superimposed actually. But what we did technically is we rotated one of the molecules with respect to this bond so initially ganyan siya. And then you rotated it this way so that they can be superimposable. So from this, we can conclude that these two molecules are actually not isomers of each other, but identical molecules. They are the same thing. If there are 4 constituents bonded to a tetrahedral carbon, the handedness of a molecule with respect to that carbon will appear. So to verify this, we can get the mirror image of our molecule and then try to superimpose them with each other. So here's my molecule. I get the mirror image. So again, there's a mirror in between them. Get the mirror image, and this time we try to rotate them all over the place to find out whether they can be superimposed with each other. So if we try this, nope, we cannot superimpose it. If you will look at it, the green atoms and the blue atoms are in the same position, but the red and the yellow ones are not in the same position. We try to rotate it. Okay, so let's try to see if we can superimpose this way. So again, just like earlier, 2 of the atoms would have the same places in both of the molecules, but the other 2 cannot be superimposable. So we can try to do it over and over again, but we will get the same result. We cannot superimpose the 2 molecules. If we go back to the first example, we can see that the molecules have a plane of symmetry. And since they are identical, I'll just take one. If we rotate the molecule and view it like this, you can see that there is a plane of symmetry that cuts through both the red and the green atom, and both sides would simply be mirror images of each other. So if there is a symmetry, there's a plane of symmetry in your molecule, then we say that the molecule is a chiral, or it doesn't have its handedness. Because if we get the mirror image of the molecule, we can actually rotate it because of the plane of symmetry. We can actually rotate it so that they can be made superimposable. In the second example, There is no plane of symmetry no matter how much we rotate the molecule because we have 4 distinct constituents bonded to the central atom. So you can't find a plane of symmetry, and therefore this makes the molecule chiral. So if you get the mirror image of the molecule, which I'm trying to get right now, to get the mirror image of the molecule, and we've already verified that they are not superimposable, then we say that we have generated a pair of enantiomers. So enantiomers are stereoisomers that are not identical to their mirror images. They are chiral molecules, as we have established, that are mirror images of each other, but are not superimposable. And they're also called optical isomers because they differ in the direction in which their solutions rotate plane polarized light. So the next question we have is, how do we know whether a molecule has a chirality center or not, or if it is chiral at all? So what we do is we check whether there is an atom that is connected to 4 different constituents, like what we did earlier with our examples, and then look for a plane of symmetry. So let's take an example. Let's consider 3-methylpentane with respect to carbon-3. So this is the structure of 3-methylpentane. And if we try to draw the molecule in its wedge dash notation and draw its mirror image as well, then we will have these 2 structures. So just from inspection, we know that carbon-3 is connected to just 3 distinct constituents. And here you have hydrogen, you have your methyl group, and 2 ethyl groups. We said that an atom can be a chirality center when it's attached to 4 different constituents. So in this case, the molecule with respect to carbon-3 is not chiral, and carbon-3 is not a chiral center. And it's true for both of the configurations. A molecule cannot be chiral when it doesn't have a chirality center. Remember, you cannot give what you do not have. So in this case, no chiral center. The molecule is a chiral. The second observation that we can get from the drawings would be the mirror images of the molecules are superimposable with each other because there is a plane of symmetry right here. So right here, if you draw it, it's right here. I will use my pointer. It's right here. So if we have the molecular model, I have the molecular model right here. Wait, now I should move this. I have the molecular model right here. And the plane of symmetry would be right here. So here are your 2 ethyl groups. You have your methyl group right here, your carbon-3 right here, and hydrogen. So if you try to get a plane, draw a plane. So you cut it from here to the back carbon, here, you cut it right there. You will have a plane of symmetry. And so you can easily rotate the 2 molecules shown here so that they can be superimposable with each other. Now let's consider 3-methylhexane instead. So here is a structure of 3-methylhexane. And this time, just from looking at the structure, we can already tell that carbon-3 is a chirality center because it is bonded to 4 different constituents. You have the implied hydrogen right there, and then you have your methyl group, your ethyl group, and your propyl group. If you try to draw the wedge and dash notation of the molecule and try to draw its mirror image as well, we will have this. So because we know that we have 4 different constituents, it's automatic that the two will not be superimposable. But if you need proof, then I have my molecular model right here. Oops. So here is your chiral carbon. Hydrogen is here. You have your methyl group, your ethyl group, and your propyl group right here. Let's make it stand like this. So methyl group is here, hydrogen, ethyl, and propyl. And then try to get the other one. For the mirror image. Mirror image is there. You have your ethyl group, your hydrogen, your methyl group right here, and your propyl group right there. So these two are mirror images of each other, and we can try to superimpose them. I'm sorry, it's not very clear. So if we were in the classroom, I would have let you play with the molecular models. But just trust me on this, they are not superimposable, no matter how hard you try. So let's go back to the drawings. As we have mentioned earlier, enantiomers are not the same molecules. So how do we know which one is which? The answer is in the assignment of the absolute configuration of the molecule. Simply put, we determine whether the molecule is right or left-handed with respect to the chirality center present, following the can-in-go pre-log sequence rules or the RS convention. So when we talk about absolute configuration, it's just the same as the RS convention or the can-in-go pre-log sequence rules. So you already did your worksheet, so you should be familiar with these rules. There are 3 important rules, so we have to follow, plus the assignment of the RS configuration. Let's go back to our example, which is 3-methylhexane. So these two enantiomers are not the same, and our task is to assign the R and S configuration for the appropriate molecule. So let's try assigning the configuration of the molecule on the left. The first step is to assign priorities to the constituents bonded to the chirality center. Higher priority is given to constituents with higher atomic numbers or with heavier isotopes. So in this case, if we try to rank the priorities of the constituents with respect to carbon-3, hydrogen will have the lowest priority, and so we give it a ranking of number 4. The other alkyl groups will have higher priorities. But to decide on that, we have to go further from the central atom because they look similar to each other. We try to find a tiebreaker atom that would have a higher priority in one of the other constituents. So this is how we try to assign priorities. So methyl group looks like this, the ethyl group looks like this, and the propyl group looks like this if we draw them in the Lewis structure notation. So we go 1 carbon away from the chirality center, and as marked in green, we can see that all of them have the same priority because they all have a carbon connected to the chiral carbon, which is our reference. If we go to the next atom, for methyl, it would be hydrogen, but for the ethyl and the propyl group, it's still carbon, the ones that are marked in orange. And therefore, methyl would have to drop out of the contest and will take the second to the last priority, which is number 3. Then now we just have ethyl and propyl. So the next atom, after the one marked with orange, would be hydrogen for the ethyl group, but it's still carbon for the propyl group. So this means that propyl would have a higher priority than ethyl because carbon is ranked higher than hydrogen. So we put together all of them. Methyl group would have a ranking of number 3. Ethyl will get a ranking of number 2. And the propyl group will get a ranking of number 1. And as we mentioned earlier, hydrogen will have the lowest ranking, which is number 4. Now we simply have to look at how these 4 constituents are arranged in 3 dimensions. So following the Can-In-Gold pre-log rules, we have to move the constituent with the lowest priority to the back and then look at the 3 remaining ones when we try to decide on the absolute configuration of the molecule. So this is the original notation that we have. And if we try to rotate the molecule with respect to the C-methyl bond, then what we will get, so we try to rotate it. Wait, let me draw. We try to rotate it. Where is my pen? I try to rotate it. I rotate this. What to make hydrogen move to this position. This one will have to move to this position, and then this will have to move to this position. So after doing all of those adjustments in 3 dimensions, we will get this. And following the convention for the wedge dash notation, we know that hydrogen would be pointing towards the back of this board. This ethyl group is pointing outwards towards us, out of the plane of the board. And then the methyl group as well as the propyl group would be at the plane of this board. And so now we can reiterate the priorities. We said that this is number 4, this is number 3, this is number 1, and this is number 2. So we ignore hydrogen this time because it's pointing towards the back, and we just look at the 3 remaining molecules. No, 3 remaining groups, I'm sorry. So if you draw the line, or draw a curved arrow, going from the highest ranked to the lowest ranked, the 3. So we go from 1 to 2, and then 2 to 3, and then 3 to 1. The direction of the curved arrow follows the clockwise direction, and therefore we assign the arc configuration to this enantiomer. So we write it officially in the name. We put the configuration in parentheses, draw a dash, and you give the proper name for the particular enantiomer that we have So in this case, this molecule would be our 3-methylhexane. This time, let's try assigning the configuration of the molecule on the right. So just like what we did before, we have to move the hydrogen bond towards the back by rotating the molecule with respect to the C-methyl bond right here. So you rotate it right there, and this one will go here to the back, this one will go here to the front, and the propyl group will go to the plane of the board. So if we try to redraw that, we will have this structure. So I've already placed the priorities of each of the substituents. And now we simply have to draw the curved arrow from the highest priority constituent to the lowest one. So as we said, propyl will have the highest priority, followed by the ethyl group. From the ethyl group, we go to the methyl group. And then we close the loop right there. This time the curved arrow goes from propyl to methyl, following a counterclockwise direction, and therefore we should assign the S configuration for this enantiomer. Just like we did before, we simply write S at the beginning of the name to specify which type of enantiomer it is. S dash, and we get the second enantiomer, S3-methylhexane. Note that chirality is a property of an entire molecule, so just because there are chiral or stereogenic carbons present does not mean that your molecule is automatically chiral. Later we will see examples with more than one chiral centers, which lead to a new kind of stereoisomers called the diastereomers. We will also see molecules with chiral centers but with a plane of symmetry, which we call the mesocompounds, and we will find that these molecules are not chiral despite having chiral carbons. So please look forward to the next video, and I hope you understood our lesson for today. Bye bye!